We're going to move on to Hassan Hijazi from Los Alamos National Laboratory, and he's going to be speaking on optimal and resilient microgrid design and operations. Hassan, whenever you're ready.
All right, thanks, Michael. Let me start with the goals that we have defined here at the lab. They are twofold. The first goal is to work on the theory and the implementation of scalable algorithms that allows us to tackle difficult problems, decision support problems in infrastructure design, optimization, and control. And this work allows us also to provide science-based input into problems of national concerns. So our team has multiple experts from different areas, ranging from physics, optimization, machine learning, and others. I'm not going to go through all the dots here, but we have experts in optimization under uncertainty, design and control of resilient networks, and others. So I would like to present some current and past projects that we're working on. Let me go to the first one, which is about the design of resilient distribution networks. The capability we're trying to build is having these distribution feeders be resilient to extreme events, such as hurricanes. And specifically, our goal was to efficiently optimize the hardening of these distribution grids under the uncertainty that comes with the extreme event. The tool we build helps the decision maker say, this line needs to be hardened, and it will minimize the effect of the extreme event. The second project that is currently ongoing is looking at remote microgrids and again helping in the decision makers in order to say what is the optimal technology mix, where do I place these technologies. So we're building decision support tools to design these microgrids at a minimum cost, but at the same time guaranteeing reliability and efficiency. And the way we approach the problem is basically we have to model it as a mathematical optimization problem. And that's the only way that allows us to provide guarantees. You can do simulation, but if you are interested in guarantees, you have to have your mathematical model of your problem and then efficient algorithms that can solve the underlying problem. So this formulation that we were looking at for this problem, we were considering at the same time the investment decisions and the operations. And in order to have an accurate model of the operations, we included in our formulations things like nonlinear power flow equations and voltage constraints, along with N-1 security constraints. The third project that we're also just starting to work on is one step forward, where we're looking at not one microgrid, but a set of microgrids that can be networked together in terms of the design and the operations. And then the motivation here is that by networking these microgrids together, you can minimize the cost and maximize the resiliency of the overall set of microgrids. So again, our goal is to improve the resiliency, the reliability, and at a minimum cost with high efficiency. Our approach is again to model this as a mathematical optimization problem, taking into account device dynamics. And in this project, we're also looking at what are the regulatory boundaries that allows these microgrids to network together. So my last slide is to highlight the common point to all the projects that we do here at the lab is this mathematical optimization foundation, basically, that provide us with guarantees that you could not achieve with simulation. So we try to, my everyday work as a scientist here is developing these efficient algorithms that can escape seemingly good solutions and looking for globally optimal solutions. We also try to have these algorithms be scalable, even though we have discrete decisions to make, which makes the problem difficult. So we have, a lot of research directions in that area. And so I'll stop here. Thanks, Mike.